All right. So let's get started. Today I want to talk about introduce the non-crossing and the one-crossing approximation for the quantum computing models. Because this talk will be recorded for later usage. So I will begin the introduction from the very beginning. And
Lei, do you want us to ask questions right away, or you want us to ask questions at the end?
right away.
Right away.
Yeah. So if you have any question, just ask me. And this is an overview of this talk. First of all, I will introduce the notations, the setup of the imputing models and the hybridization expansions. Second, I will introduce how to derive the self-consistent equations for the hybridization expansion. And third thing, I will introduce how to do the measurement. Finally, I will introduce my NCA OCA solver, how to run that, and what every parameter means. So let's get started. So for the quantum computing model, it usually has three parts: each local, each base, and each head. For each local, it means the Hamiltonian for the impurity. It usually has two parts. One part is the non-interacting hopping term, and the other is the interacting term. And by the way, we should be careful about this notation. Usually we use IGLK, not IGKL, in our simulation. And each base is the Hamiltonian for the base, which is quadratic. And each half is the coupling between the impurity and base. And the parting function is the trace over this e to the minus times the total Hamiltonian. And we can separate the total Hamiltonian into two parts, HA and HB, and express the parting function in this time ordering representation.
You said that already. Your notation for the H1 local is very much non-standard. Right?
Yeah.
UIJKL, DI dagger, DJ dagger. That's very different from how it's.
That's standard. It is right that you have to have KL here, but LK in the other.
That's right, but okay, fine, go on.
This is in 1122 notation, right?
Yeah.
Actually, that's what we use in ED and
but this is how all our Hamiltonians are listed. So it's precisely true that one has to be careful not to say IJKL and then IJKL.
That's right, but our UIJKL would be UI. Well, anyway, okay, let's move on. Yeah, one has to be careful.
Okay.
You just have to define it.
Okay. Yeah, and next I want to introduce what the hybridization expansion. So in hybridization expansion, we treat HA the background as H local plus H base, and HB equal to H hat. So in the background, there's no coupling between H local and H base, and we do the Taylor expansion regarding to HB like this. And it can be simplified by some complicated calculations. And here, I have a note for the detailed derivation. If you want to look through the derivation, I will. This note will be uploaded on our homepage later. So here I will just briefly introduce how to do that. So this expression can be simplified according to the following observation. First one is for the coupling Hamiltonian, it has two parts. This H tilde have and H tilde have dagger, and for each term, it only contains one base operator C or C dagger. Because we finally need to do the trace, the total number of the base electron has to be conserved. So that means the only even K. The only even term with equal numbers of H tilde tab and H tilde tab dagger can make a non-zero contribution. And also because we treat HA, the background, as H local plus H base, there's no coupling between the base and the impurity in the background. So they can be decoupled from each other. So the trace over the whole thing equals the trace over D times the trace over C. So they can be decoupled from each other. And finally, we notice that in the background, the H best is corrected for the best electron. So we can use Wick's theorem to simplify the expression. So far, any questions? Okay. And this is the definition of the hybridization function in the imaginary time. If you can do a Fourier transform to get the I omega, you will find they are consistent. And after the definition of this function, so this is the final form of the hybridization expression. It's a little complicated. So
Lei, what's the epsilon value?
Sorry?
Because you have like this V the
here,
yeah,
you mean the epsilon k?
yeah,
like
like
that.
on imaginary frequency would be like V, right? Like delta ij would be V I k times V kj, right? Divided by omega minus epsilon k.
Yeah,
So
here,
epsilon k.
because we are doing the average over here. The epsilon k comes from this one.
All right.
So non-interacting Green's function can be written as, 1 over frequency minus pole location.
Right.
That's exactly that Green's function.
Okay.
Yeah, this part contains the epsilon k. Yeah. And okay, so this is a final expression of the partition function in the hybridization expression definition. So the configuration space is a little complicated. It's mainly described by 3 parameters. K is the order of our expansion in the Taylor expansion. Tau means the tau is a vector tau. It means the time for the D and D daggers here. D and D daggers. And by the way, the D's and D daggers are time ordered separately, but there's no specified the time ordering relation between D and D dagger. And the J is the corresponding flavor for each operators. And this is an exact result as long as this perturbation is not infinitely large. So if we perform the CT-QMC, we will get a numerical result, numerical exact result. So we can do 2 steps. There are mainly 2 methods to perform the simulations. First method is CT-QMC. So we sample each configuration according to its weight, W local times the determinant of delta. This method is numerically exact, but it may suffer from severe sign problem, leading to the exponentially growing errors. And the second method is called self-consistent resummations of diagram in the literature. That's what it's called in the literature. And the NCA and OCA are 2 frequently used methods. The benefits of the second method is it will not suffer from sign problem, because we only need to iterate 2 self-consistent equations later. And another benefit is the computational cost only scales polynomially in the system side.
Is that correct? Lei?
Which
Is
one?
that correct?
Which one?
The computational cost scales polynomially in system size?
I think so.
Well, the Hilbert space grows exponentially, all right? And with that,
Yeah, but this sentence I read this sentence from a literature.
well, that doesn't mean it's correct, right?
Yeah.
That's a bad justification. But I think what was meant here is that it grows polynomially, as a function of temperature, for example.
Yeah.
But as you add new orbitals, this becomes exponentially more expensive,
Yeah.
as you've seen yourself, right?
Yeah. It was this will scale 2 to the 2 times the nth power.
Yeah, so I would be very careful with this, that it's at least a little bit more exponential.
But it's still more efficient if it has some problem. And finally, the disadvantage of this method is it's not numerically exact, and it's also not easy to estimate the systematic errors. Okay, this is the warm up, and let's go to more details. Let's go to more details of this self-consistent resummation method. First of all, to derive So the main goal is we want to find the self-consistent equations for the hybridization expansion representation. And to do that, we first need to expand the configuration space by a little bit. So you may remember that in the expression of the hybridization function, we have this term, the determinant of the hybridization functions. It has k factorial terms. And we expand that, we can solve that as k factorial terms as a possible pairing between tau and tau primes. And then for each pairing, we just represent the curves connecting to the corresponding pairs. And these curves called the hybridization lines. What that means is we expand the configuration space by introducing one more degree of freedom. That degree of freedom is the pairing between tau and tau primes. And you can write down its contribution as follows. Yeah. And after we expand our configuration space, we can define the pseudo particle propagators. The bare propagator equal to the e to the minus h log tau. And the rest propagator is actually this expression is very similar to the hybridization expansion of the partition function. The only difference is we remove the trace. So if you take the trace, you can recover to the partition function immediately. And this is a typical configuration of the R tau. So this is the third order, one-third order configuration. We have 3 times tau 1, tau 2, tau 3 for the Ds, and tau 1 prime, tau 2 prime, tau 3 prime for the D daggers. And tau 1, tau 2, tau 3 are time order. Tau 1 prime, tau 2 prime, and tau 3 prime are also time order. But the time ordering between tau and tau prime are not specified. And we also need to pair different D and D daggers. Here in this example, the first D is paired with the final D daggers, and also you can see that. And also for the hybridization line, you can understand that as follows. So at time tau 1, there's one impurity electron hop into the base. And finally, at tau 3 prime, this electron hop into the impurity again. And if for the left arrow, you can consider that as at this time point, the base electron hop into the impurity, and until tau 3, it hop back into the base again. Any question? Okay. And after we understand the configuration of our tau, we can construct any configuration as follows. Step 1, we just choose an order k. Step 2, we specify the values of vector tau, which fulfilling the constraint that tau and tau primes are time ordered separately. And finally, we pair tau and tau primes using the hybridization lines. And for each configuration, you can write down its contribution by the following. It equals an overall sign, which will be analyzed later, times the contribution calculated from this small segment. And you should be careful that in our diagrams, the right direction corresponds to the time increasing. However, in the expression here, because the conventional t tau, the left hand side corresponds to the time increasing. So you should be very careful about that. And the overall sign comes from 2 places. Place 1 is the time ordering between D and D dagger operators, and the second part is the pairing between tau and tau primes. And I will show you later a very straightforward way to determine this overall sign. Next, we want to find the self-consistent equations for the graph propagators. Equation 1 is straightforward. It's Dyson equation. That means S is the self-energy of the corresponding pseudo particle propagators. And S is a set of all one particle irreducible diagrams. And our question is, we want to find another equation to connect S and R again, so that we can iterate to get a convergent result. And we noticed that the structure of S tau is very complicated because it has many crossover points. And so we need to do some approximations to get a simpler expression.
So I should probably say here that you call this the Dyson equation, and that's probably
maybe
certainly with this figure here, it's clear that it is of the structure of a Dyson equation. But it's very different from the Dyson equation in like the usual in imaginary time formalism. Right?
So I call here pseudo particle.
Exactly, it's really a Dyson equation for the pseudo particle propagator. So it's a very weird object if you're coming from standard diagrammatics. So just as a word of warning, but it has exactly the same structure.
Yeah, maybe I just I think. So we need to do some approximations to get another equation connecting S and R. So here comes the non-crossing approximations. For this approximation, we only consider configuration without any crossover points. So that means the D at the very beginning must have to be paired with the D dagger at the very last. Otherwise, it's not irreducible, or it must have some crossover points, or D dagger D, the reverse order. And also the sign will be analyzed later. The second approximation is a one crossing approximation. So it's a higher order. It's a higher order improvement for the NCA. In this approximation, we consider the configuration which has at most one crossover points with all otherwise. And we can analyze its self-similar structure and write down this complicated expression. Finally, I will introduce how to determine this overall sign. So in the literature, people usually use the Latin word functional to analyze that. But I found a more straightforward way to do that, to analyze the overall sign. So the main idea is to find the connection to the following configuration, which we know has a plus sign. So this configuration is tau 1 prime less than tau 1 less than tau 2 prime less than tau 2, etc. And the ice D is paired with the ice D dagger. From the first thing, we know that the sign coming from the time order of D and dagger is +1. From the second one, we know that the sign from the determinant is also +1. So we just want to find the connection to this configuration. And to do that, I found we need to do two elementary movements. One is we need to move a prediction line across a coordinate graph. And another is we need to switch the order of this hyperdensity. And I found that the first step will not change the sign, and the second one will change the sign. You can find more detail in my notes if you are interested. And just examples. As we use this that two elementary movement, we can find the expression of S tau, S0 tau and S1 tau, the plus one and S1 here easily.
Another good way. You unplugged there. Another way, a good way of finding these things.
Yeah.
Oh, okay. Is the trace has to be cyclic. So if you take one of those vertices and you move all of the vertices by the same amount, so that one wraps around to the beginning, then the sign has to stay the same. And that's a good way of debugging your signs and also checking that you're getting the right.
In the next slide, I will introduce some more appearance. So when we use that to elementary movement, I can prove this fully statement. The conclusion one is if we want to get the expression of S tau, we just need to replace R by R0 in the self-energy expression. Evaluate this, the overall sign in this case, and then replace R0 by R again. Then we will get the correct result. And the second one is to get that overall sign, we just need to count how many right arrows and crossover points to get the overall sign. So why we use right arrows, not left arrows? That's because here in the expression of the hybridization function, we use C dagger. If we use C dagger C, then we will need to count the left arrows instead. Okay. And because these two simple conclusions, we can even do improvement over NCA OCA. We need first of all, we need to choose an order. And if n equal to 0, then we will get NCA. If n equal to 1, we will get OCA. And n equal to 2, we will get a subset of the two crossing approximations. So we can write a MATLAB or Python script to get the analytic expression for that. But currently, because OCA is already very slow, so maybe not, it doesn't have much usage. So far, any questions?
Maybe also comment that the inchworm method is, something very similar, where at zero crossing or cutoff at order 0 or order 1, you get NCA. Cutoff at order 2, you get OCA, and then you can gradually converge inchworm. And we have cases where inchworm has to go to very high orders. But we also have cases where the system is not really hybridizing that much, where inchworm actually converges very fast. So Andre is an expert for any sort of question on that.
Yeah. Also, we are doing the parallel programming of sure. Okay, let's continue. Let's say I want to introduce how to do the measurement. So here we already get the self-consistent equations 1 and 2. Then what we need to do is iterate these equations and get a convergent result of the pseudo-particle propagator. And after we get that, we can do the measurement. For the static quantity, because we know whether we take the trace over R, we will get the partition function. So we can get the static quantity easily by doing the trace. And we can also evaluate the dynamical quantity. For example, the single particle green function using these two expressions. This one is for the NCA, and this one is the improvement for the OCA. And I should say that. So that's what I use in my code, but there's a disadvantage. The disadvantage is for these two equations, they don't take the vertex correction into account. So the solution is just consider the vertex correction. However, the theoretical idea is very simple. So we just need to calculate the vertex correction. However, to do the program, to make the code, is almost unaffordable for multi-optical cases, because we need to enumerate all the input and output states, and it grows exponentially. So currently I just use these two expressions for calculating the single particle green function. Okay, finally my code for the NCA OCA solver. So I call it XCA solver because X can be a variable. Maybe it's on the GitHub here, and the dependence of my code, it depends on two libraries. Library 1 is the XCore, and library 2 is the eigen library to use the matrix operation feature in that. And to run my code, you only need to do 3 steps. Step 1, you need to prepare the input file, which I will introduce later. And then you need to change the input parameter accordingly. Finally, you just run this shell script, which means you use CMake and make build the product and run this. this code. And for the input, so that's why I have also introduced the notation here. So for the input file, currently it supports two kinds of input. One is it completely compatible with the ED, so the ED input. This is the correspondence between this theoretical expression and the corresponding data notation. Here, be careful that this is the convention in ED input is ij sigma, not sigma ij, and it's also compatible with this is the data given by China. I think it comes from the GW simulations, and this is also the correspondence. So here we use sigma ij, not ij sigma, and the interaction is only dependent on the orbital index, regardless of sigma prime. And because different software has different formats, so my plan is to write a Python script to get a uniform input format to run my code. And the output of my software are the top mesh and the single particle brain function, which has this convention. Ij are the orbital index, sigma I, sigma j are the corresponding spin index. And this is all my input parameters in my code. This column is the real value I used in the simulation of the EG orbital of the magnet outside. And the first one is the number of orbitals. The second one is the number of spins. Currently, my code only supports spin one half system, but if needed, I can generalize that later. The third one is the beta. This one is the system temperature. Max iteration is the maximum iterations I use in the NCA or OCA iterations. And precision is just the precision of this solver. So if once we reach this precision, the iteration will stop. And this one is the number of slices. Currently, I use the uniform mesh, but maybe I will use non-uniform mesh later. This one you should be careful that this n slices is the number of slices. It equals the number of time points minus 1. So by the way, for the number of top points, 0 and beta are included. And this operator to determine whether we need to do the cutoff or not to detect the symmetry. And this one is whether we choose to perform the SC symmetry. If we say it's true, it will detect the SC symmetry. If the SC symmetry is not conserved, then the code will stop and warning used to set this to false. And this just whether we choose to run NCA or OCA. This parameter is discretized, means whether we need to discretize the best. If it is equal to false, then the input should be the delta function directly. If it is equal to true, the input is epsilon k and vk. And finally, the input and the output file here. Any questions about that?
I should probably clarify that there's never any need to discretize the hybridization function in NCA or OCA. But if you want to check against what, for example, exact diagonalization gives for a certain discretized version of NCA of hybridization, you can artificially introduce the fitting errors into the NCA and then compare to what the ED gives for the same problem. The whole thing is a trade-off, right? NCA is an approximate method, but it doesn't suffer from any bad fitting or bad discretization error. And the ED, of course, is an exact method for a discretized hybridization, but it suffers from the discretization error or the fitting error of your hybridization. And at the moment, we don't know which one of those problems is more serious. So that's one of the reasons why we're looking at this now with these NCA OCA solvers.
Yeah, and maybe I will write a Python script to if we fit the best, maybe I will do that before input to the C++ code. And here's the notation I use. So the first entry of the state is the upstream state in the zeroth orbital, and downstream state in the zeroth orbital, and the upstream state in the first orbital, etc. This is the notation I use in my code, and I labeled these different bases as follows. So I just take this as a binary expression and calculate its decimal expression of the value, and then that's the corresponding label. So 0, 0, 0, 0 is 0, 0, 0, 0, 1 is 1, like this. That's. And I don't use here I just did a little modification to accelerate the calculation of the block diagonalization. So here is I will introduce how to do the block diagonalization later. So the main thing is to find the transformation matrix to change the order of the bases. And we notice that I noticed that this matrix is a sparse matrix, and the all the entries is all the non-zero element is equal to 1. So so it can be simplified it can be accelerated to calculate this transformation in the new basis.
Keep all the up and down strings together, right? You don't separate them.
Sorry?
You keep all the up and down strings, right? For all the up and down electrons together. You don't separate them, right?
So you allow for off-diagonal hybridizations. I think that's the question.
No. So for example, in a non-relativistic approach, you could separate all the up and down spins, and then take the resulting matrix is a direct product of them.
Oh.
So in the non-relativistic thing, one can do it like that. But for example, if you wanted to work with relativistic Hamiltonian, then keeping them together is necessary. So
you mean the upspin, if we group this data as upspin and downspin, it will be block diagonal.
Yeah. So it will be block diagonal, and your dimension of Hilbert space would drop, right? Because you will not need to have that product. But if you want the relativistic case, then you cannot separate them.
Yeah.
So
I think I didn't separate them.
So that's okay. One can do the relativistic Hamiltonian directly that way. But I think if we wanted to study non-relativistic case, it may pay to separate them, because then your dimension of the Hilbert space would drop a lot.
So yes, and there are other things that one could also do here. There's a bunch of optimization that we can go through. I think that's a second step, because first we have to establish how useful this technology is, because we don't know how bad the NCA OCA approximation is going to be in practice.
But people do.
Well, the fact that people did some of these calculations before doesn't mean that it's a good approximation. Also, people never did off-diagonal hybridizations with any of this. So that's
what do I know about the OCA and NCA for like doing numbers, like how are they work?
If you're in the insulating regime, it's fantastic. If you're not in the insulating regime,
means like not, or means like
doesn't matter, right? Anything away from the Fermi surface, this thing doesn't hybridize. It's great. Anything that is dependent on subtle behavior at the Fermi energy, like Kondo peaks and things like that. The height of the Kondo peaks are off. The width of the Kondo peaks are off. Like it's not a technology that gives you like very subtle correlation physics at the Fermi energy. But it might just be good enough for many of the applications we have. The non-interacting limit in these things is very difficult. So non-interacting in the sense of U equals 0, right? Because U equals 0, you hybridize the most, particles fly all over the place, and the approximation gets bad. But the moment you have some sort of blocking in your system or some sort of fan insulator, this works very well. So if you think of the F electron systems, for example, where you just have F electrons lurking around, but you're not actually participating in you know, any physics, this should be fantastic.
But if this is really the magnitude of the hybridization that matters, then I don't know, like if you transform Hubbard to different bases, just should be much better. Is that true? That if you did the Hubbard in the, the bases that got like not in right on-site orbitals, but the linear combinations which diagonalize the hybridization into these 2x2 blocks, that already should become better.
I don't know. It not clear to me.
Currently, I just use the observation basis, and this is the how to do the block diagonalization. So the symmetry usually depend on the exact form of each local. But usually, we know that the total particle number and total SZ spin are conserved. So what we need to do is switch the order of the bases so that this with the same N and SZ are grouped together. And after do that, the each local is block diagonalized the follows, and it should be faster than before. And the data structure I used in the block diagonalization is here. I use math vector. So for example, for this matrix, I use a vector which has 16 elements. The element 0, 5, 10, and 15 are this matrix. And the other elements are 0 by 0 matrix. Why I also slot the blocks here? Because also for the each local and the R0 is block diagonalized. But for the D and D dagger, it's sparse, but the net zero element is not in this block. It's in here or here. And for the dress propagator R and the self energy, it may or may not can be block diagonalized depending on the system you simulated. So this is the uniform format I use in my code. And I also use some operator overloading so that this whole vector can be can be do the addition, multiplication, scalar multiplication, and constant shift directly. So if you want to use the block diagonalization in other solvers, maybe you can just you use my code in this part. So because I have an exam right after the talk, so not right after, several hours later. So I think I will stop here and open to any questions.
All right, thanks.